Also es ist mir eine große Freude, diesen Kurs zu halten. Ich muss sagen, dass ich also wenn ich das nehme, was der Stefan gesagt hat, dann ist es so fast eine Story, wie jemand die Wüste zum Wachsen gebracht hat, und irgendwie sehe ich es auch so. Sorry, okay. So just get the question if the course is in German. No, I think I should do it in English. Yes, thank you for the hint. So it's like growing a vegetable in the desert, and it's true that when I was a young assistant, Jacques Dieudonné, the well-known author of the analysis books, in French analysis books in the Bourbaki style, was visiting Vienna, and especially Hans Reiter, and he was telling us, well, you know, harmonic analysis or abstract harmonic analysis is off-stream. So there's not much to do. I mean, convergence problems for Fourier series are not fashionable. If you look now into time frequency or wavelet analysis, you see, well, there is still a huge amount of open questions. And what I see mostly is we have to go more and more into applications. And I have learned myself a lot from the applied people. So making contacts to the people from communication theory in my case, or image analysis in medical sciences, was already something that really made NuHAG strong and will continue to be relevant. Now, I thought, how can I describe the variety of topics that I plan to describe in this talk? And I was choosing the following picture or the following idea. We look at the castle, and kind of nice old castle, and or you're fascinated about castles, and then you can ask very different questions. You can ask, who has planned it? How can we plan it? But how can we fabricate it? How do we actually build it? Who has financed it? Why is it built at this place? How is it connected to the other examples? Or if you take a tour through the castle, you're saying, oh, that's so nice inside. Well, how is the decoration going and so on? But who will pay the maintenance or take care of the maintenance, the renovation work? And so in Gabor analysis, you have the corresponding questions. How did it arise? How can you perform it? What are the tools that you need? And I will try to touch as many of these questions, but of course, this is not a coherent thing. It's not about a renovation of old castles. It's not about a historical tour or so. So in that sense, it's a bit mixed up, and I hope inspiring for you. Okay, so Gabor analysis is seen as a part of time frequency analysis, and sometimes the definition of the field is made by the observation that you have time shift operators, which are unitary operators on L2 space, or energy preserving operators in the signal analysis terminology, and you have frequency shifts, which are multiplication with pure frequencies. You will get the details later on. And everything that you can do from these building blocks can be viewed as time frequency analysis. And Gabor analysis is a particular branch where we are dealing with discrete representations as opposed to integral representations. But let me, before going into details, start with one or two historical slides. In the last century, we have seen the development of what I call the technical basis for Fourier analysis, or so. Fourier was suggesting that every function can be expanded, every periodic function can be expanded into what we call the Fourier series nowadays. But these days, neither the concept of a function, what is a function, in the modern sense, it was developed only in the 19th century. What kind of convergence can we have? How do we compute the integrals? And by the advent of Lebesgue integration in the beginning of the 19th century, not 20th century, sorry, of course, it was possible to work with LP spaces that you all know. Especially with L2, you have a Hilbert space structure, or you have LP spaces with P between 1 and infinity, and they are reflexive Banach spaces. So you are dealing with what I would call non-finite dimensional, sometimes called infinite dimensional vector spaces. And in order to say what you talk about expansion, you need convergence of infinite sums. So we are talking about series, and that's where linear functional analysis is coming in. Now, we all know that there is a big problem with pointwise convergence in L1. The integral and the Fourier coefficients are well defined, but you may have problems with pointwise convergence everywhere, according to Kolmogorov. But you can, with a lot of technicalities, prove almost everywhere convergence, as Carlson was doing it for L2 functions. So it's a very difficult subject, and more or less, for me, indicates that LP spaces and Fourier expansion are not well fitting to each other. Wavelets actually are much better related to LP spaces over Rn. Now, I have marked a few references, and you can access most of these references in the literature. So Gabor was saying what we call now should be a Gabor expansion already in 46. This is a family which is an expansion into Gauss functions which are shifted in time frequency. We will see this in a moment. The corresponding theory of non-orthogonal expansion by the example of not harmonic Fourier series expansion. So think of an expansion into pure frequencies which are not related by arithmetic progression. So like a microtonal piano, but not equidistant tuning. This was already done in the work of Duffin and Schaefer, the origin of frame theory. But these two papers have not been connected earlier than maybe I would say 86 in the fifth reference, which is a paper by Ingrid Dubschi, Alex Grossman, and Yves Meyer, where they did painless non-orthogonal expansion. A paper where you can learn a lot about frames in the Gabor and in the wavelet setting. And there's a big distinction between wavelet and Gabor, and that's due to the Balian law principle, which I don't discuss in detail. So what was the idea of Gabor? Dinesh Gabor was suggesting to expand every function, we would say nowadays every L2 function, at least in some distributional sense or so, as a double sum. There's an I missing of the Gauss function G shifted along a lattice with lattice constant A and modulated with cosine and sine, so e to the 2 pi I missing B and X. So the frequency lattice is characterized by the lattice constant B and the time lattice by the lattice constant A. This is the standard Gauss function, which is normalized in the L2 sense. It's normalized in the L1 sense. It's normalized in the L1 sense because it's such that the Fourier transform, and I take the Fourier transform with the 2 pi I in the exponent, leaves this function invariant, so everybody can see that G0 of 0, of course, is e to the 0, it's 1. So that's why the L1 normalization is okay. The subnorm normalization is okay, but in the L2 norm, it's a little bit, you have to renormalize it. Now, his argument was choose the Gauss function because it's so nice, so well concentrated, both in time and frequency. And if you would take A times B larger than 1, you would not be able to approximate even arbitrary L2 functions. That's true, even if you replace it by another function. While for A times B less than 1, you're losing uniqueness. And that's kind of true, but if you try to stay with A equal B equal 1, then you have problems of both kinds in a mild form, but it turns out to be not exactly what he had in mind. So he was saying that these coefficients tell you how much time frequency content you have at time position AK at frequency Bn, but what he was overlooking was that not every function can be expanded as a norm convergent sum, And also these coefficients are not locally obtained, so they are obtained in a rather nasty way. So the finding of modern Gabor analysis is, with all the attempts that we had in the last years, well, you have to live with redundancy. So don't care about the problem of non-uniqueness. Actually, if somebody has a linear system with too many variables, then you just take the solution which has the minimal norm. And then you can still find some coefficients, the best possible coefficients, the solutions of the minimal norm least square coefficients. And then you have uniqueness in a different way. So it's not uniqueness a priori, but by the choice of the minimal norm coefficients. So this is what nowadays is viewed as the prototypical Gabor expansion. Now, once you see this question of expanding a function, you can ask yourself a large number of questions. I put a few on this slide. First of all, which functions should be represented? L2 is the first choice, of course, but then you would say, well, every L1 function, every LP function, every locally integrable function, I think that would be too much. Every tempered distribution with convergence in the distributional sense. So the bigger the reservoir is, the more you would allow in this convergence different types of convergence. So the question is is it meaningful to discuss convergence in the pointwise sense? First answer, in principle, not so much, because it's the same problem as with Fourier analysis. Or, well, the Gauss function has infinite support, at least theoretically. Can we replace it by a compactly supported function? Is the smoothness of the Gauss function important, or just some form of smoothness? Actually, you will see that cubic splines, for example, which have compact support are quite fine also. Well, in a modern terminology, you would say, well, maybe Gabor was hoping to have a respaces. And the respaces in a Hilbert space like this one is like a basis in Rn. You're saying, well, I have an orthonormal basis like this, and you deform it a little bit. So you're starting with an orthonormal basis in L2 of R or Rn. Then you apply an invertible mapping, but which does not preserve angles, and then you're getting all the possible good bases, which are called respaces. Every such respaces has a bi-orthogonal respaces, and which is like the inverse matrix in the finite dimensional case. But the answer is essentially no, you cannot have it, except you're allowing yourself nasty functions, like the boxcar function, the rectangular function, the indicator function. But we will see that this is not very good and not in the spirit of Gabor. So can we discuss the same in more general setting? And the answer is very well, yes. You can do it for any locally compact abelian group. And if you choose, for example, a product group of two finite abelian groups, you're discussing Gabor analysis for pixel images. Pixel images of format, I don't know, 400 times 600 or so, can be developed in a computational way using MATLAB very nicely. And the theory is more or less the same, except that you have finite systems and there is no convergence problem. You don't need any function spaces, any fancy type of convergence. So that's why I will illustrate this also. Now, one of the questions asked to engineers once I showed such a representation was, how do you compute the coefficients? So that's definitely an interesting question. And another question would be, well, can we choose other lattices or other point sets? And the answer quickly given now already is, we can choose any lattice in the phase space, in the product space, or in the one-dimensional case. I mean, for audio signals, you can say in the complex domain, you choose any lattice, any grid, that can be a hexagonal grid even, and you can do Gabor analysis replacing this standard grid, the separable grid, by these things. And but it's not allowed or not reasonable or not advisable computation, much more expensive to choose irregular sets. So you can do it, but it's more Now, I wanted to say also a few words to the relationship with wavelet theory. Wavelet theory is working in a similar way. You're choosing not time frequency shifts of the Gauss function or something like this, but you're applying a different group, a group which preserves the shape of the graph. So you have a function, you're shifting the function and you're dilating it. So you're applying affine transformations, the so-called AX plus B group. And I call pi lambda of G so simply G lambda. So we have building blocks which are sitting at certain positions and have certain widths, the big broad ones which are quite flat, the very concentrated ones obtained by compression, so with A either smaller or very big. And then people, I mean, even Meyer, Ingrid Dobschi, and so were able to produce orthonormal bases. This came as a surprise at that time, but everybody can use an orthonormal system, because if you're asking how can we expand a function f, then the answer is the coefficient corresponding to one element in the orthonormal basis is just the scalar product. So that's like in Rn. And we even have Parseval's relationship. So the lengths of a vector can be obtained by the coordinates in such an orthonormal basis. This is now an infinite sum of squares, but it's really just the same. So in the wavelet theory, the big thing was we can construct orthonormal bases. We have systematic development. It's still quite interesting also, but everybody can use it. Now, the Balian law principle tells us not only was Gabor not so lucky with his choice, I mean, it was very inspiring to many people, but it would be fine to have a Riesz basis which has the structure that he was supposing, but Balian law says, no, you cannot have it with this good time and frequency concentration. Now, are all possible orthonormal bases equal or equally useful or so? And the answer is a mixed answer. I mean, I'm choosing the Fourier transform in the standard way. Here the minus is missing. I will have to correct this as well. And I can see that the Fourier transform is having eigenvectors. These eigenvectors are the so-called Hermite functions. So already Norbert Wiener was observing some almost 100 years ago that the Hermite orthonormal basis I mean, the operator that you use is an unbounded operator, which is called harmonic oscillator. That's not important. That this gives a very interesting, very useful orthonormal basis for L2 of the real line or so. And now you could say, well, what can we say about these orthogonal expansions? What kind of function spaces can we characterize by the decay of the Hermite functions or so? And I must say, even nowadays, for a long time I was saying, well, it's such a historical object, it's not very useful. You're changing a function a little bit at one place, and you may have an influence on many, many Hermite coefficients. Well, nowadays I would, unlike Gabor or wavelet expansion or so, nowadays I'm a little bit more careful. I would say this has not been studied so well, and the corresponding function spaces might be interesting or so. But each time you have an orthonormal basis, you can ask, well, how much does it depend on the situation? How much useful is it? And here the wavelets had a big advantage, namely at the time when wavelets were appearing, there was a very well-established theory of Biesov-Tribole-Sorkin spaces by the pioneers of interpolation theory, Jacques Petre mostly, and Hans Triebel. They were trying to say, well, if you try to interpolate between one of these Biesov spaces and another Biesov space, or a Sobolev space or so, how can you describe these functions? And they discovered that with dyadic decomposition of the Fourier transform, you can get a much better understanding of these function spaces, which were originally designed as generalized Lipschitz spaces. So this is a whole area. The point I want to make is that only in this area, the spaces were here, somebody found these wavelet bases, and then they found out, oh, we can describe all these function spaces by the behavior of the coefficients in such a wavelet basis. So it's not this unique basis which can be used, but there are many similar bases. All the good wavelet bases with wavelets satisfying sufficiently many moment and decay conditions can be used to characterize all the Beer's spaces up to some order or the special potential spaces. And the second good thing is, if you do this expansion and you're saying, well, I want to throw away the small coefficients, you're guaranteed that the partial sum, so this sparse approximation, is still convergent in the same space. So throwing away such wavelet coefficients which are small, which has approximated a function very well in a Beer's space norm, then the approximation is taking place in the Beer's space norm, and it's not like approximating a smooth curve by step functions or so, which is not so useful, as we know. Now, a similar story cannot be told about the function spaces related to Gabor expansions, which are the so-called modulation spaces. It was a bit in the opposite direction. I don't want to spend too much time on the history, but here the theory of function spaces had to be developed, and the theory of expansion has to be done first. So just to give a glimpse on these earlier papers, I was referring to the books of Treibel, this quite interesting book of Jörg Petre, and of course the differentiability properties of Stein. And the first book which started to bring in Wavelet theory is of course the book of Yves Meyer, who was receiving the Abel Prize later for his work. So just one short slide. Balian-Low theorem prohibits the existence of these re-spaces, or especially there are no orthonormal bases, even if you play around and try to replace the Gauss function by some more fancy object. And that's why we have to decide whether we want to expand functions, all the functions. Then we are going with frame theory. We have to live with redundancy, or we emphasize uniqueness of coefficients. And that's again interesting for communication theory. We want to transmit information. Roughly speaking, the idea is information can be obtained by putting a harmonic accord with the piano. And if I play such an accord, and if you are able to analyze it, the loudness, you're able to recover the information, the digital information in the signal. So assume I'm playing sufficiently slow and at scores which are well separated, then you could guarantee the recovery of the coefficients that I was using. I've called this the so-called piano reconstruction theorem long ago. It's a very easy idea, but it shows you the two sides of Gabor analysis. We will emphasize the spanning side or so. Also, there are the early papers, just to give you a time scale of wavelet and frame modulation space theory. So all this started in the late 80s, where the atomic characterizations, which later led to wavelet theory, appeared, mostly interesting papers by Fraser and Javert, inspired definitely by Jörg Petre and Treibel, and where I was starting to play around with these function spaces, which have some modulation operator built in, and that's why I call them modulation operators. Independently, at that time, Gabor's idea were picked up by a person in optics, Martin Bastians. And the first mathematician who until now has contributed a lot to the field is Guido Janssen, who was trying to save the idea of Gabor by saying, well, maybe he's right by allowing distributional convergence. And then it turned out, well, you have to be very careful. Nowadays, I would say, it's not only that you are making the convergence more vague, but you are also restricting the attention. So only nice function can be expanded in a distributional way exactly following the rules of Gabor with the formulas obtained by Bastians. But what you cannot have is uniqueness and representation of everything. So he was also showing that you can have distributional convergence by bounded sequence, which is representing zero in a non-trivial way as an infinite sum. And there are the applied people, Daugman and Zevi, and I met both of them in around 1989 or 9 at Harvard University. And they were trying to connect the idea of Gabor with the idea of vision systems. So the visual system, the visual cortex, had some similarity with their ideas, and that was a very inspiring period or so. So I was already telling this to you, and let me mention some phrases that you find in early papers on Gabor analysis. They were very often using the following sentence. Well, you observe that the Gabor family, these time frequency shifted Gaussians, are obviously non-orthogonal systems. So just think of two Gauss functions. If you shift them apart, the scalar product definitely is never zero because they both have infinite support. They are both non-negative. They may be small, but not perfectly orthogonal. So this is a true statement. Yes, they are non-orthogonal, and therefore it's like inverting a non-orthogonal matrix must be difficult. So that was a standing assumption for quite a long time. I must say, with the work of Sigan Quiu in the early 90s in Vienna, that it's really the spirit of NuHAG and we were starting to do it with MATLAB, and we were looking at the matrix. We were observing, oh, this matrix is not a random matrix. It has a lot of structure. And that, of course, paired with observations of other people who tried to compute Gabor coefficients in the finite discrete setting, turned out to be a very good basis also for intuition for this thing. So the situation is, it is not orthogonal, so you have to look around for the structural elements, try to understand them as much as you can, and make use of these properties, which are not in other theories, in order to do efficient theory and also good code, efficient coding. And the second thing is that the idea was very much focusing on the original situation, which is nowadays called critical sampling. So with A equal B equal 1. And in this case, the situation is that you're getting an unstable representation. Now, I would say, if we have time, I will do this linear algebra experiment. You're just missing one dimension. Of course, if you're missing one dimension in an infinite dimensional space, it's like nothing. You don't see a big effect or so. But I met John Daugman, and he was showing me images reconstructed from this well-known Lena image with 2D Gabor, and I was trying to say, well, you see, in each dimension you're losing one dimension, and that's explaining a lot of the artifacts that you get in your reconstruction. So we have overcome this. Now, I have worked a lot in time frequency and Gabor analysis, and I would like to give you an outline of a series of papers that were made such that we can follow it. One is the paper with Tobias Werther and Franz Luev, which from 2007, which tries to say from linear algebra to Gabor analysis, so a bit in the spirit of this course here, trying to avoid infinite dimensional Hilbert spaces, function spaces, convergence problems. But there is a lot of structure in these problems, and they are described in this paper with Kotzek and Luev on the algebraic background. So if you have a finite abelian group, you can do Gabor analysis. So the intersection of those two areas is, of course, Gabor analysis in a linear algebra style for finite vectors, and that's what I will show in a moment. And then it turned out to be necessary to go to continuous or continuous non-compact variables. So in a real line already, or the RD, the Euclidean space, you should work with 3 objects, not just the pure Hilbert space where you don't see certain effects. Clearly, you see some instability, so to say, but you see much better what happens if you go to the smaller so-called Siegel algebra, and that's the mentioned Fichting algebra, and it's dual space, which I try to promote as the space of mild distribution, because it's really a space of distributions, but they're rather mild. And you can think of acoustic signals like what we transmit when you listen to my talk now. These are all elements from this space. We can compute spectrograms of these guys. They don't have to decay at infinity or so. They don't have to be point-wise well-defined everywhere, but there are things that we can measure. So the sound produced by my voice is, for me nowadays, such an object, a generalized function. Well, you don't have to worry about this. It's a physical signal, an applied person would say, and I can record it, and I can expect if I raise the voice and increase the loudness, the coefficients will be correspondingly amplified. And so for a good understanding of Gabor analysis, I think we have to work at these 3 levels. And already anticipating my approaches, I would say it's like rational, real, and complex numbers. Once you are trained in mathematics, you're not worried about changing from computations first in the rational domain. Then you say, well, but the real numbers are better. You have square root of 2, pi, and other objects. And sometimes it's really convenient to go to the complex numbers, and you always think of any rational number is a decimal number. Any real number can be viewed as imaginary number. Sometimes complex exponential functions are more useful. So you're moving around identifying objects. So my statement, roughly speaking, with this Banach-Gelfand triple is, S0 is the domain where you have decent function, maybe in a very classical sense. Continuous functions, Riemann integrable, which you can draw, which have a Fourier transform, which is invertible, everything is fine. L2 theory allows you to express energy preservation arguments. You take limits, you make it complete like you make rational numbers complete to get the real numbers. And this is where you can understand what's really going on, or what the objects that you really need to treat with can be measured. So it's not pointwise by the procedure of pointwise almost everywhere. So these are the concrete references you can get to these things. So I will switch now to the other slide. And hopefully try to tell you more about this now from a linear algebra point of view. Now, again, this will be provided as PDF file, and I have a habit, which is kind of going back for a long time, to view signals as row vectors. So maybe you think of yourself as a medical doctor who pins the different pictures on a light wall to see the picture. So if we would see signals, you would have a graph, and then the first graph and the second graph and so on. So, and that was my original intuition. Now, if you use MATLAB as I do, and this is a live script, you think that, well, signals should be column vectors, because if you, for example, you want to plot 5 signals, put them as columns into a matrix, and you get the right plot or so. So sometimes it's a disadvantage, but I see also some advantages, and I want to make it short. So the point is, I'm afraid of confusing things or things not working if I would use standard matrix multiplication. So I'm using the row column mode is rowed in my things. I can do it in column mode as well, but so I think it's too dangerous to change it on the fly. So the classical situation would be you have matrix multiplication of the form AX is equal B, and we all know what it means, that A is a linear mapping moving X from Rn to Rm, or in the symmetric case of the square matrix, moving X to B. But it's also quite important to see that X can be viewed as a list, an ordered list. So you're doing a shopping list and you're saying, okay, please give me x1 times the first column of A plus x2 times the second column. So the linear combination, it's producing a linear combinations of columns. So when is this such an equation solvable in general? Well, if and only if B is in the range of the mapping, which means the linear span of the columns. And so if somebody says, well, this is an invertible matrix, how can we get back from this B to the unknown coefficients x? And you, of course, multiply with the inverse of the matrix. But the inverse, of course, we think this is matrix multiplication with an inverse matrix. But we can also say, no, what you're doing is you're determining the coefficients. How do I get x3, the third component or so? And then, of course, you would say, yes, I have to take the third row of the inverse matrix. Think of this matrix called matrix vector multiplication, and take a scalar product with the vector B. So in order to determine 5 coefficients, x1 to x5, you have to have 5 row vectors. And these 5 row vectors taken as a scalar product on the B give you the coefficients, assuming everything is uniquely determined, for example. So what can you say about the rows of the inverse matrix? Well, inverse matrix times matrix is identity. And this is expressed as a bi-orthogonality relation. The row in the inverse matrix with a certain number paired with the column of the same label is giving 1, and all the other scalar products are 0. So we are talking about bi-orthogonal systems. So MATLAB does not have a command for scalar products. So if you're doing it with row vectors, then, and I'm showing this here in the experiment, then I'm choosing 2 row vectors of length 1, Euclidean length 1, and equal column vectors. So it's just a transposition, a column version of the same vector is here. Now, how do you express the scalar product? Usually written as U with V. So first comes U and then B. And the B is, if it's complex valued, a conjugate. So you have U1, V1 conjugate plus U2, V2 conjugate, and so on. If you write it with column vectors, look at this, you get this number. This is the second term. You have to take the second one into the first position. Then this is a row vector, but there's the conjugation, and that's why the V has to come first. So it's a bit flipping the arguments. Whereas if I work with row vectors, it's very simple. I have to recall, well, you want to compute the scalar product of U with V. So I'm taking the U, row vector, make the V vector, also row vector, into a column vector. So the comma here is transpose conjugate, and it will be conjugated, and you have this natural order as you have it here. So maybe you would say column vectors are more like for physicists who like to have a scalar product antilinear in the first converted, but we are mathematicians. And just to show you, it's the same, of course, the result here, but I think it's more intuitive to say work in this order. Also operators, we are having matrix multiplication. What is A times B doing on a vector X? Well, you first have to apply the B and then the A. So you have always the flip. Whereas if I multiply from the right, is just first you apply one operator, then the next operator, and there's no flip in this. So it's not what we are used, but I think it's more natural in a way. I think it's also good to recall that a scalar product is a projection operator. So if you're doing matrix multiplication from the right, what you have to do, if somebody is giving you a unit vector, you take a scalar product, that's a column vector, and then you're saying multiply with a number. And of course, this is in the matrix calculation, an n/1 matrix multiplied with a 1 pi n row vector. So by what I call the domino principle, so you're composing 2 matrices, in this case, the generate matrices, is giving you a matrix which has format n/n. But that's exactly what you expect from a projection operator. So to see that this is really a projection operator, I just take the square. So I call it the projection onto the row vector named U, and it's really the difference is numerically 0. I take a random vector and I say, well, if I take this expression here, the random row vector under the projection, this is the projection matrix, is of course numerically again the same as taking first coefficients, that's building the scalar product of this unknown vector, and then multiplying with this. You have to observe that this term here is good in terms of understanding what's going on, but this is much more efficient. Here you have matrix vector multiplication, whereas here you have matrix scalar multiplication. So if n would be huge, that first part would be much easier than this one. And if you think you would do the same thing now with ordinary matrix multiplication from the left, you would have a much slower thing, because MATLAB automatically puts this, even if I would not put the brackets, it would first compute this here and then compute this here. And in the transpose way, it's much more expensive. But okay, so that's fine. Now, we're having the pure frequencies in Gabor expansion, and that's why I'm calling now next the situation which I use for all these Gabor expansions. Most of the time, I prefer to use n equal 480. This is a number which is close to 512, but in a sense better, because it has quite a few prime factors. So clearly it has a prime factor 3 built in, 5, and so it has many more different divisors than 512. 512 is a power of 2, it's 2 to the 9th. But so all the divisors are other powers of 2 only, whereas here you have big choices in the number of divisors. That's important because we need such divisors of the signal length. Now, the discrete Fourier transform is implemented in MATLAB in the form of the FFT, the fast Fourier transform. And in order to understand what the Fourier transform is doing, is you just have to know here that the Fourier transform is applied to a matrix is the same as applying it to the collection of column vectors. Now, I of n is simply the unit matrix of order n. So applying this column-wise just tells you what the images of the unit vectors are, and they turn out to be exactly the pure frequencies. So they are complex valued, therefore I plot only the real part, and you see they are cosine function. Cosine of 0 is the blue line here. Cosine of 1 time is a cosine curve here, and so on. So you have now 5 different frequencies, and the confusion or something you have to be careful is the frequencies are starting, of course, with 0. You see the blue line, 0, 1, 2, 3, 4. And 4 is already the one which has the highest oscillation, in my case, the green curve, but it's number 5 in the list. So you have to always think that you cannot have a vector or a matrix with a zeros component. You can do it by labeling it in abstract mathematical formulas, but in MATLAB, 0 is taking the position of 1. So you have to be careful with this. Now, of course, I can also plot the real part, imaginary part, and I have a routine called plot C, which not only does this, but also it puts 0 in the middle. So instead of having from 0 to n, it goes more or less from minus 240 to plus 240. And you see very well, number 7 in the list is, of course, a function which has 6 oscillations. So we have 1, 2, 3, 4, 5, 6, because this is already the partner of this one. And you could wrap it up on a cylinder. So take this piece of paper, wrap it around I don't know, toilet paper or so, and you will see that you have a nice graph. And the cosine part is the real part, and the red part is the sine part. So you have cosine plus I times sine, which is exactly Euler's formula. And so these are just exponential functions with increasing indicators. Now, this plotting routine applied to what I call my discrete Gauss function of the same length is giving such a plot, which is kind of not nice. You would like to see it in the middle or so, but with the plot C command, we just, without changing the order of the data structure, so to say, I mean, I'm talking about data structure versus visualization of the data. For the plot, it's better to use the plot C command, which is C for centered. So plotting it on this way. Now we have another nice command in this live script. It cannot rotate it or so to tell you why it's such a convention or so. We have to think of any such signal as a periodic signal. So if it's wrapped up on the torus, you see such a picture. So this is a so-called, I think, a Henning window of size 32. Now, if I would be able to rotate it, you would say, oh, that's very simple. It's just cutting the cylinder by a plane, and the plane is made such that here it should touch 0 or so. And here it has some height. Of course, if you unwrap it, you are saying, well, the first coordinate, well, where do you start? We start at 0. The first coordinate is 0, and then you go up and you go down, and you are having a symmetric function. So if I show such a function now in my plot C command where the 0 is put in the middle, you are getting such a graph. So you get an impression in the same way. Maybe it looks a little bit shifted, but okay. Now another command using the auxiliary command, this command for visualization is first the low signal command, a command generating a signal of length n with maximal frequency 20. And the F2 spec command is show me two functions, both in the time and the frequency domain. So we are showing in this picture here a Gauss function and its Fourier transform. Actually, we are not showing the Fourier transform in the sense of FFT, but FFT divided by square root of n, because then we have an orthonormal change of basis. So it's really a unitary mapping. So you shouldn't see a difference between this, and numerically it's exactly equal. So I'm mentioning that this is obtained from the classical continuous Gauss function by appropriate periodization, which is kind of irrelevant, and periodic sampling. But you're not sampling from -5 to +5, but you're starting to sample from 0. So it's the sampling should occur in this way. You're starting at 0, and then you're doing a regular sampling until the end of this period. And from the other side, you're sampling this. So the last value here in your discrete Gauss function should be equal to the second value, because the first value takes the role of position at 0 in such a circular way. So this is a symmetric function because this value corresponds to the same value on the opposite side and so on. So this is how you should read these pictures. Now, the function which is here taking random coefficients at 0 and 20 positive and 20 negative frequencies is looking like this. So you have a real part, imaginary part, and the Shannon sampling theorem viewed in this picture would say, if I sample this function not too much, I would see a repetition of the spectrogram here, and that can allow to recover it. Now, why are these Henning windows or windows so interesting? I just mentioned it because normally you don't get exact full period, but you get from such a function, you get a piece of it. You would like to analyze it. So you say, oh, it's a smooth function. You should only get certain frequencies. But if you take a piece, so I was really taking a piece, and with the plot C command, you see here at 0, there's a jump. Well, because the random fragment that I took out, some vector of length 100, the end, which are kind of arbitrary, don't fit. Even if you would take a pure frequency and you're not synchronized with the frequency, you have a jump. And that jump makes these side lobes, so it's moving out of this, and that's not good, and it's much better if you put a 0 here. You could compare the Fourier coefficients of the short piece or so. Yes, for every pure frequency you have some small error, but the spectrogram, so the distribution of frequencies would be much more as you would expect them. Okay, now we have the Fourier matrix, and we know what shift operator means. Of course, you're moving your Gauss function. Now I'm telling you just by pictures, as a picture book now, what a time frequency shift is. You're shifting the function in time, and it means that you're modulating with a frequency. So if you're shifting here with 30 pixels in a cyclic way, you're multiplying with a frequency which has 30 oscillations on the full domain. Of course, on the support of this Gauss function, the Fourier transform of Gauss is Gauss here, it has only a few oscillations. So you have to think the total number of oscillations over the full signal length would be 30. Now, I don't have a command for pure modulation, but I have the command rotmod, which means rotate and modulate in the order of first rotate, then modulate. The G, and I don't rotate, but I modulate by frequency 20. So I take column or row, it's a symmetric matrix of the Fourier matrix number 21, and I multiply my function with this, and then I see on the Fourier transform, it's just a shift. So this is what transposition is in music. You're playing the same melody at a different frequency. You're singing the same melody, but a higher tune or so. Now, you can check the details of this part here yourself. For example, that rot mode with frequency 7 is really the same as, so it's really here, it's frequency 7, whereas here I take multiplications with the actually it's the inverse Fourier transform, because the Fourier transform has a minus, so it was a typo, and therefore I have to take the conjugate, and it's number 8 because I'm starting with 0 as the first row and column. So here these are just tests that, for example, the inverse matrix here is, if I multiply the Fourier matrix, the matrix realizing the Fourier transform with its conjugate, we know that this is the plus, it's Fourier synthesis, and I compare this matrix with the unit matrix, the comp-norm routine, which I use so often, is just saying, well, maybe I'm getting the same signal or same matrix, but with a different scaling. And yes, the first one is having different by the factor n here. But if I normalize it, so I put this to length 1, this to length 1, then the difference is 0 in the numerical sense. So it's like numerical precision of the system. So that means if I would change it and would say, well, divide by conjugate with 1 over n, so that's what I'm here, this is the inverse matrix. Now, I can also, the command to build those matrices, TF matrix is constructing a matrix which is of size n by n, realizing the time frequency shift by 3 first and 5 afterwards. So this is just a test. I can apply my rot mode routine, or I can do it by first multiplying with the corresponding number. First by rotating it, and then the rotated version is multiplied with frequency 5, which is the conjugate of this here. So you see it's, or you're comparing here the rot mode command with matrix multiplication, and I told you I'm doing it from the right. Again, the error is perfect, it's correct normalization, and the error is 0. Now, I will maybe use the last few minutes to show you that you can expand functions into irregular Gabor families, and with the following story. Here I have, this is a random pattern, so each time I repeat it, I get different numbers. I'm choosing 964 elements. So let's say it's roughly speaking 2 times n, but they are irregularly spread. I'm constructing a collection of such Gauss functions where for each point, now each point has an offset in the horizontal and the vertical direction. So if I choose this point here, I would count how much offset do I have. If it's like 20 or 51 columns away from the first column, which represents 0, I would say the time shift should be 50, and it's a row number or something, and then I get two numbers. Then I would say for this point, I add into this family a time frequency shifted version of my Gauss function, so the ones that we have seen. And so I get my collection of 968. For each red dot, I get one Gabor atom. And I can ask, well, what is the quality of this? Are they, and that's the standard question of Gabor analysis, are they spanning all of the signal space, all the vector space of n-dimensional, 480-dimensional signals, viewed as functions on the unit roots of order n? And the answer is, yes, not so bad. The condition number is just 41. Now, and because I'm coming close to the end of the time, I would like to show you a little bit intuition or so about these Gabor families. I would say, well, I create a two-dimensional Gauss function, which is just a column version of the Gauss function with the frequency. And I'm now taking this random pattern, and you can imagine if this would be the plane, I would put a 2D Gauss function at every point, and then I'm summing over all these Gauss functions. Now the landscape I'm getting from, in this particular case, now the red dots are turned into black dots, and the landscape is this. So red means high mountains, blue means relatively low valleys or so. So what you see immediately here is that here in the mountains you have a lot of dots. Well, it's clear here you have accumulated a lot of Gauss bumps, whereas in this sparse area here in the middle of this, you have only the side lobes of these, and so they're very close to zero. And so essentially what you can say is, depending on how rough this landscape is, how high the biggest mountain is versus how deep the deepest valley is, this is related to the condition number. So we could play around, repeat the experiment, and if the distribution is very irregular, then you would get maybe condition number like 500 or so. If you're very lucky, it's very regular. Of course, the most regular cases are these lattices. So we will see that it's very reasonable, and that's kind of the A-B case in a discrete way. Here I was choosing A, some divisor of n, in this case it's 20, A equal 20. So that's here. I'm choosing A equal 20 and B 16. And I'm getting that for this we have 720 lattice points. This is another lattice which is not so rectangular or so, and both of them have redundancies 3/2. We are creating 3/2 of this 480, which is 720 building blocks. And so essentially when we study Gabor analysis in a finite setting, we're saying you have to, it's a good idea to choose an element which is structured in this way, and we have to understand how to balance the shape of the lattice with the building blocks, or whether it's a Gauss function or a flat Gauss function, and so on. And so I think I better stop at this place, and I mean I will stop the recording, and please feel free to ask questions.